Let's discuss in this video L'Hospitals rule. We know this theorem from calculus, it's very useful, but we are going to see it in a slightly different way that we are used to. Here, the main point is the last statement, that when we have a quotient of two functions, f of x divided by g of x, the limit of the quotient of the two functions equals the limit of the quotient of the derivatives. This is not the derivative of a quotient, it's a quotient of derivatives. Okay, there are some conditions. This theorem applies when both functions f and g have limits, have a limit of 0, both of them, or the limit of the denominator is infinity. It could be also negative infinity. Okay. So this applies to indeterminate limits, and it's a way to resolve indeterminations whenever the functions are differentiable. Here, the part that may be a little different from what we are used to see is that we are taking lateral limits as x tends to a. A is the left limit of the interval. It could also be the right limit of the interval. That would not be a problem. Okay, so this is a slightly more relaxed than the usual hypothesis we are used to see in the calculus books. Okay, and the other thing that is a bit more relaxed is that here we are requiring that the limit of the denominator only is infinity. Okay, we are in either of these two cases. But sometimes we see that this is applied when both f and g tend to infinity. Here we will show that only the denominator needs to go to infinity. Okay, one thing I wanted to comment, just for the fun of it, is that this guy, L'Hospital, was a French nobleman, and he was this rule was actually discovered by I believe Jacob Bernoulli. If not, then it was his brother. And this guy L'Hospital was paying for the research, so he got credit for this theorem. The same way that today we get research grants, well, it was the equivalent of the time. Anyway, let's work with the proof. I'm going to do the proof in a slightly different way from the book. The book, you can read the proof already the way you write it once you are done. The way I'm going to do the proof is just showing why we are doing things. So it's going to be lengthier, but it will probably be more insightful. Let's call a, capital A, the limit as x tends to lowercase a of f prime of x divided by g prime of x. And let's assume for now that this capital A is a finite number. I will mention the adjustments that are needed for negative infinity or infinity. So let's assume for now. Okay, anyway, our goal here is to show that if A is in between two numbers P and Q, then the quotient f of x divided by g of x is also between those two numbers. Remember, a is the limit of the quotient of the derivatives as x tends to a. Okay, then what we are going to do, we are going to shrink P and Q to a, and that will give us the result. Okay, that will give that the limit as x tends to a of f of x divided by g of x equals a. Okay, that is the general strategy that we are going to follow. Here, of course, there is no hope that this is going to hold for every x. Okay, so something that is going to be important in this proof is that most of the things we are going to do will be only for x close enough to a. Okay, and this close enough, we will need to see what that means. The way to make that precise is by using carefully the definition of limit in terms of epsilon delta. Okay, so close enough will mean for delta small enough. Okay, so let's get to work. So here, let q bigger than a and choose some number r such that r is in between a and q. Then remember we have that the quotient of the derivatives converges to a as x tends to lowercase a. By definition, that means that there exists some number c in AB such that f prime of x divided by g prime of x is less than r. Well, let's write it with letters. For all a less than x less than c. Okay, here let's do a picture that will help. So this is our limit a, and then we have q, and r is something in between. Okay, and here something to keep in mind is that r plays the role of epsilon, c plays the role of delta. Okay, in the definition of limit of a function. Now, here we are in a position that we can use the extended mean value theorem. Okay, we just need to take two between a and c. Okay, notice here that this is already giving that idea of x close enough to a. Okay, so between a and c, we are going to pick two numbers, x and y. And then the extended mean value theorem is going to say that there exists t in xy such that, and here we just need to be careful, okay, such that f of x minus f of y times g prime of t equals g of x minus g of y times f prime of t. Here, of course, we are using that both f and g are differentiable in this interval. Okay, they are differentiable in the interval AB, so then in particular, they are differentiable in AC. So we can rearrange. And we find that fx minus fy divided by gx minus gy must be equal to f prime of t divided by g prime of t. Okay, now one thing here. G prime of t, we know that it's different from 0 by hypothesis. Okay, gx minus gy, we can assume the difference is different from 0. Okay, if not, we just shift one of the points a little bit. Okay, one thing here, this quotient is less than r for sure. Okay, r here, let's copy this. Because t is less than y, which is less than c. Okay, so that means, again, remember the way we define c. C was such that the quotient of the derivatives was less than r, okay, for every x between a and c. So there we go. Here we are using this property I just said. Now, in the statement of the theorem, there are two options. We have two sets of hypotheses that we can be using, and we will use either of them. Okay, so here we need to branch out and do two tracks, one for each of the hypotheses. Let's do first the limit of f of x equal to the limit of g of x as x tends to a. These limits both equal to 0. Now, written like this, we have fx minus fy divided by gx minus gy. The limit as x tends to a is going to be, so we have 0 here, sorry about that, 0 here and 0 here. So we get negative fy divided by negative g of y. Okay, but we might as well write it with a plus. Therefore, because fx minus fy divided by gx minus gy is less than r, strict less than r, then fy divided by gy is less or equal than r. And that is what we were aiming for. So here we have fy divided by gy less or equal than r, which is less than q. By definition, we picked r less than q for every y that is in between a and c. Okay, so here this is the first part. Notice, let's go back to the goal we had. Okay, we wanted to show that if a less than q, then fx divided by gx less than q for x close enough to a. That is precisely what we have proved. Here we have that for every y, now I'm saying y, but it's the same as before, okay, just a change of letter. For every y that is close enough to a, this close enough is given by this number c. There exists some number c. Then fy divided by gy is less than q. And here I want to comment on this less or equal. Okay, this is the reason why we take this r less than q. Okay, because in the definition of the limit, if you notice, the inequalities are strict. Okay, so if you want to get a strict inequality here, then you need to put this r as a buffer. Okay, because when you take the limit in this step, you will get a less or equal. So if we didn't take r, here we would have found less or equal than q, but we wanted strict. So that's the reason why we took a little buffer. Okay, so that's just a little calculus trick, analysis trick. More of a technical detail maybe. Now this first track, we are good. Now the second track, here we assume that the limit of g of x is plus infinity. And we want to reach a similar conclusion. Okay, so let's see how we do in this case. Now, as before, let me copy paste from here. As before, we can show that fx minus fy divided by gx minus gy is less than r. Okay, this we proved before branching out the proof into two tracks. Okay, so this we can still use. Now here we want, always remember what we are aiming for. Here we want fx divided by gx less than q, or f of y divided by g of y less than q. Either of the two works. Okay, but let's say we want to keep y fixed. Okay, so we are going to aim for this one over here. Now, when we keep y fixed, we can manipulate this quotient and write fx minus fy less than r gx minus gy. Okay. And then we can leave fx alone on the left. And we get this inequality, fx less than fy plus r gx minus gy. And that's it. Okay. But remember, we want to be able to say something about the quotient fx divided by gx. So we can divide here. Okay. Both sides plus r gx divided by gx is 1 minus gy divided by gx. Okay, and here the idea now is that as gx goes to infinity, this term here is going to disappear, this one too, and we get fx divided by gx less or equal than r. Okay, so that's which is less than q. So that's basically the goal. But there is something I was not very careful in this argument I did. So there are two problems in these few lines. First one is here, and the second one is here. Okay. Now, what is the problem? So did you notice here that to get this first equation, star 1, I multiply the whole thing by gx minus gy. Okay, but because the inequality stays the same way, I'm implicitly assuming that gx minus gy is positive. Because if it were negative, the inequality would flip. Okay, so we need gx minus gy positive in star 1, and we need gx positive in star 2 for the same reason. Okay, otherwise the inequality will switch. Okay, so otherwise the inequalities will flip around. So we need to take care of that. But that is where we are using the hypothesis, right? That g of x goes to plus infinity as x tends to a. Okay, this means uh, since y is fixed, doesn't really matter how large g of y is. Eventually, as x tends to a, g of x will be so large that it will be positive, g of x, but it will also be bigger than g of y. Okay, so that's where we are using it. Here, let me do one of these pictures. So here we have our A and C. Remember, we are already working close enough to x, close enough from the first step of the proof, the first track, means that x is in between A and C. Okay, but now also, because x is less than y, and y is less than c, we are working actually on the interval a y. So the fact here, the fact that g of x tends to infinity as x tends to a means by definition that there exists c1 in a y, okay, let's say somewhere here, such that if x is less than c1, then g of x minus gy is positive and g of x is also positive. So then we are good. Then star 2, this one here, let's actually copy paste. Holds, well, for every x in a C1. Again, this means for every x close enough to a. Now we can take limits as x tends to a. Okay, so as x tends to a, well, let's do first the right hand side. Because y is fixed, f of y divided by g of x becomes 0, and g of y divided by g of x also becomes 0. Okay, so we get here, well, the whole thing will converge to r. So what we get is that the limit as x tends to a of f of x divided by g of x is less or equal than r, which means it's also in particular less than q. Well, actually we can write f of x divided by g of x less than q for x close to a. But here again, what does it mean close to a? Okay, that means that there exists some C2 in AC1. Let me do again the picture here. So we have A, we have C, we have Y, we have C1, and then as X tends to A, we need to find some other number C2. Okay, that is close enough. So there exists C2 in AC1 such that, because we know that the limit of the quotient is less or equal than R, and R is strictly less than Q, for sure, as X tends to A, there will be some point where f of x divided by g of x goes below Q, okay? Because it has to reach R, which is strictly smaller than Q. So such that f of x divided by g of x less than Q for all x in A C2. Let's create some space here. Now, notice here we reach the same conclusion. Either way, both tracks give f of x divided by g of x less than Q for all x in A C2. Okay, here it's to make this work in both tracks at once to make it elegant. We have done this trick of always reducing, keeping C that makes track 1 work, and keep reducing it until we make track 2 also work. Okay, in this way, it doesn't really matter which track the proof takes. We will know for sure that the conclusion is still valid. One thing I want to note here, this argument works the same if A equals negative infinity. Okay, so if we want to do, remember in the beginning I said let's assume for now that A is finite. If A is negative infinity, this also works. And then that would finish the proof. Now, similarly, we can show, remember that we wanted P bigger than A. So for P bigger than A, we can show that P is also bigger than fx divided by gx if x is close enough to A. So we take C3 that guarantees that, okay? For C3, we are going to reduce further the C2 we already found. We do this because we want both of them to hold at the same time. Okay, summarizing, what we have here is that given PQ such that A is in between P and Q, there exists C3, which is a function, well, it depends on P and Q, okay, such that the quotient fx divided by gx is in between P and Q also. Okay, that is what we wanted to show to start with. Now, notice here, this C3 is not independent of C2. Okay, we are taking C2 and reducing it further if needed, just to make sure that we have both inequalities at once. Otherwise, we would have one or the other. And now we can take both PQ because they are arbitrary, we can shrink them to 2a and we are done. Here it's very important that P and Q are actually arbitrary. We didn't choose them. We just picked some, okay, that were on either side of A, but that was it. One thing that I want to mention is that here this argument for P covers A equal plus infinity. Okay, so the same way that the argument for Q covered negative infinity, the case of plus infinity is covered by the argument for P. That is the last detail in the proof.